Before we begin this lecture, are there any questions from last time? What we did last time was we completed the section on tokenization and linguistic pre-processing. We saw a set of techniques that could be combined in any way you like, depending on what particular system you're trying to build. We looked at stemming tokenization, and after looking at linguistic pre-processing as a whole, we then moved on to see how we can speed up the merge operation, the intersection operation on the postings lists using skip pointers by augmenting the postings list with skip pointers so that we can um, do the AND query at least in sublinear time. And towards the end, we started looking at um, how we can augment the inverted index we built in chapter 1 to handle phrase queries and proximity queries. And we looked at one solution, which was to use a byword index, where instead of indexing every individual token, we index every pair of consecutive tokens. And that allows us to answer phrase queries. Two-word phrase queries, of course, can be directly answered using this index, but even longer queries can be answered by breaking them down into consecutive pairs of terms. And we saw that this can have certain false positives. And the other problem with this was that the size of the index blows up because if we start combining words in pairs, then we can have a much larger number of pairs of words, because of which the size of the dictionary would blow up. So we saw that even though byword indexes may not be used on the whole corpus, we will see later in this lecture how we could use some of the ideas from byword indexes into what we'll be discussing now, which is positional indexes. So we can combine both solutions to get the best of both worlds. So this was a summary of the last lecture. Do you have any questions at this stage?
No questions.
Okay. So recall that in the first chapter, when we talked about the term document incidence matrix and the standard inverted index, we were not keeping track of how many times various words appear in documents, and we were not keeping track of their positions. We are simply keeping track of the presence or absence of words in documents. Now we are going to change that because we saw last time that this kind of an index cannot be used to answer phrase queries. So we are now going to augment the index and start storing positions of words in documents as well. And these indexes are called positional indexes. So what happens in a positional index is that if you have a term, let's say this is a particular term in the old dictionary, and let's say you have some postings list. Now this picture is a little misleading because as we saw earlier, these lists are actually implemented as a continuous run of postings on disk. In main memory, one could use linked lists, but conceptually they are lists. But I'm showing them in this way because you can think of the the addition that we are going to do in a positional index as not only recording the doc ID. So far, every entry in the postings list was a single integer, which was a doc ID, and of course, a pointer to the next node in the list. Now you can think of each posting not only recording the doc ID, but also having another list inside it, a second level list, which will record the positions at which this term occurs in this document. So for example, if the very first token in this particular document, let's say this is the document with doc ID 3, if the very first token in this document was this particular term, whatever that term is, let's just call it T, then the first position would record a 1. If 10 words down the line this term again appeared in the document, then we would record 11, and so on. So we are recording positions at which this term occurs in this document. So think of a positional index as being represented in this particular way. You have a particular term, and of course, along with the term, you are maintaining the document frequency as before. But you have these postings lists. So this is the first entry of the postings list. This is the second entry of the postings list. This is doc 1. This is doc 2, and so on. But along with doc 1, you are storing another list recording the positions at which this term occurs within doc 1. And you are recording the positions at which this term occurs within doc 2, and so on. So suppose we take a particular entry in the index. Let's say we take a word like B, and its document frequency is pretty high. Uh, Probably this index was built on a corpus of size something like 1 million. So almost 993,000 of them have this word B. Now, this word appears in document number 1, it appears in document number 2, it appears in document number 4, and it appears in document number 5. And within document number 1, it appears at these positions. Within document number 2, it appears at these positions, and so on. Now, suppose we were searching for this phrase, to be or not to be. Which of these 4 documents could contain this phrase? So note that we are just looking at the word be here because this is just a single term that we are looking at in the entire index. So this is the term, this is the postings list. Is it possible to filter out those documents which definitely won't contain this phrase? What are the good candidates among these 4? Can you speak louder? Somebody said,
Four.
yeah,
Four.
yeah, 4 and 5 is the right answer because in document number 4, so the way you check what is a good candidate is by looking at how far these two occurrences of the word be are from one another. So they are separated by 4 words. So does document number 1 contain a pair of occurrences of the word be that are separated by 4 tokens? Well, no, the difference between 18 and 7 is 11. This is 15, and so on. Document number 4 contains such an instance, and document number 5 contains such an instance. Document number 2 doesn't contain. So 4 and 5 are good candidates for having this particular phrase, although that's not necessary because we don't know what the intervening 3 tokens are here. They could be these 3 words or they could be something else. But at least we know that 1 and 2 are not going to have this phrase. So let's see how we can use such a positional index to answer phrase queries. So consider a phrase query like Stanford University. We want all documents containing the word Stanford and the word university such that the position at which the word university occurs is exactly one more than the position at which the word Stanford occurs. So what we will do is we will follow a similar procedure that we followed for the standard inverted index. we will look at the word Stanford in the dictionary. We will look at the word university in the dictionary, get the postings lists for both these terms, and once we get the postings lists, we'll start traversing them just as we were doing before. We will start looking at what are the doc IDs for in the Stanford posting list and what are the doc IDs in the university posting list. Now, if a document has to contain this phrase, clearly that doc ID of that document needs to appear in both the lists, just as before. So we will again have two pointers walking through the two lists, doc ID by doc ID, and in exactly the same way. So that if there is a document which contains both the words, the two pointers will reach that doc ID at the same time. But it's not sufficient for a document just to contain the two words now. We also need to check that the two words appear adjacent to one another, Stanford appearing just before university. So once we hit the same doc ID, we will now have a second walkthrough where we will start walking through the we will start walking through the positions at which those words appear within that doc ID. So let's say this is the word, let's say this was the word university, and let's say we have the word Stanford somewhere else in the dictionary, and that has its own postings list. Now assume that this first document with the doc ID of 3 contains both the terms. Now we need to check whether both the terms appear adjacent to each other or not within this document. So we will have two pointers now, one walking through the positions here and the other walking through the positions here. And now we are going to increment these two pointers very similar to how we were incrementing the two pointers that are walking across these doc IDs. Except that we want the difference between the two pointers to be exactly 1. So we can modify the walkthrough algorithm to do a second walkthrough with a slight change. We want P1 to stay exactly one step behind P2. So that if both P1 and P2 are at positions such that the position of P1 is exactly one less than the position of P2, then we are going to append this document with the doc ID of 3 to the answer list. Is that clear? Intuitively. We now need to deal with more than just equality of doc IDs. Equality of doc IDs is a necessary condition, but it's not a sufficient condition because we need to check in addition to uh, the equality of doc IDs that that particular document contains these two words as part of a phrase. So, for example, this longer phrase query to be or not to be will be answered by treating it kind of like an AND query. You want all these words to be present and you want them to be present one after the other. So when checking, so what are the four terms generated by this query? To, be, or, and not. So let's just look at the first two, to and be. We are going to filter out the documents which contain the words to and be such that the word to occurs exactly before the word be. So let's say this is the postings list for to and this is the postings list for be. If you look at the first entry, they don't match. So if you have two pointers over here, Initially, this pointer will be pointing to doc ID 2. This one will be pointing to doc ID 1. Since 1 is smaller than 2, we'll increment this pointer and it's going to point now to the doc ID 4. Since 2 is less than 4, we'll increment this pointer. Now it's going to point to doc ID of 4. Now the doc IDs are the same. That means this document number 4 contains both the words to and be. But does it contain them right next to one another? For that, we will now have another um, pair of pointers doing the walkthrough inside the postings here. The positions over here. So we start from 8 and 17. We want the position of 2 to be 1 less than the position of B. That's what we want to keep track of. So we will try to ensure that this pointer stays exactly one step behind this pointer. If it turns out that this pointer is lagging behind this pointer by more than one step, then we will increment this pointer. But if we find that this pointer has reached exactly at the same position as this pointer or has exceeded it, then we are going to increment this pointer. And when will we output something to the answer? When we reach a pair of values such that the difference between these two is exactly 1. So right now 8 is much less than 17, so we'll increment this pointer to point to 16. Now 16 is less than 17 by exactly 1. So this document does contain the phrase to be. But does it contain the entire phrase to be or not to be? Well, this pair is not a good decisive pair, because if you look at the next occurrence of the word to, it's 190. Right? We wanted the next occurrence to be separated by just 4 places. So we're not going to output this to the answer. We will increment both pointers simultaneously now because the difference is exactly 1, and that is the condition. This is analogous to the case where the two doc IDs were exactly the same in the normal walkthrough. Now we are going to increment both the pointers if the difference between them is exactly 1. So this will come to 190, this will come to 191. Again, we find that there is the phrase to be over here, but then the next one is too far away. So this entire phrase couldn't be there. So we'll again increment both the pointers simultaneously. Now we find that 291 is much less than 429, so we increment it. And now we get 429 and 430. So again, we've detected the phrase to be. But now if you look at 4 positions ahead, we find that 433 is part of 433 is separated from 429 by 4 units, and 434 is separated from 430 by 4 units. So now we have detected these 4 occurrences which fit in with this particular pattern. So we'll append this particular document with doc ID 4 to the answer. And of course, we'll then need to take that answer list. That answer list is going to be an intermediate list which will need to be intersected with the OR list and the NOT list, again keeping in mind the positions. So this is how we process a phrase query using positional index. And we follow a similar method for proximity searches as well. For proximity searches, the difference between the 2 pointers is not going to be 1, it's going to be k in general. And in fact, it could be k either way. So it's possible that, so if I say that the word Brutus should appear within 7 words of the word Caesar, recall that this was the Westlaw syntax we saw in chapter 1, then it's possible that Brutus could appear before Caesar, or Caesar could appear before Brutus, but the distance between them should be less than or equal to 7 words. So that was a proximity query, and we can answer proximity query using a more complicated variant of this algorithm. So, any questions about phrase queries? using positional indexes.